All right. We can slowly start the second half. I hope you've all had time to stock up on fuel. If not, please go ahead. And yeah, let's dive into categorical deep learning. We have covered a lot of ground in a relatively short amount of time, but it is hopefully sufficient for us to now see how all of this relates to geometric deep learning and how it will help us discover new deep learning architectures in a constraint-driven way. So, as we said in the previous slide, we can use this group action monad to track which group action we are performing on our individual items, data of interest. But we haven't told you yet how to execute this group action, actually. To do this, more generally speaking, if you have an object that allows you to execute computations stored inside other objects, in category theory, these kinds of constructs are generally known as algebras. Okay? And one thing that's very important to note about execution, and you've already seen this throughout the course, by the way, is that executing a computation might happen differently depending on what is the object you're acting on. So when we talked about permutation symmetries acted differently on node feature matrices, which were of shape nodes by features, and on adjacency matrices, which were on shape nodes by nodes. Right? We transformed the first using Px, where P is a permutation matrix. We transformed the other one using PAP transposed, right? So the way in which your group action will transform an object changes depending on what that object is. And as a result, we don't talk about one algebra, which acts everywhere in my category, but we talk about an algebra relative to an object, which we call the carrier object, as you will shortly see. So let's define this idea of an algebra. So we already defined a monad, and we showed that group actions can be reasoned about using a monad. So let's assume we have a monad to start with. And we also have a pair of an object and the morphism, big A and little a, in our category, such that A is the carrier object. So that is the particular set or particular object on which you want to act using this group element. And this lowercase a is a structure map morphism that maps M of A, so Endofunctor transformed object, to its basic form object. And this is basically something that allows us to execute that last step of computation. Of course, this must be done in a way such that it satisfies certain constraints. And once again, these are the diagrams that need to commute in order for this structure map to be a valid algebra. And you might see that these diagrams look very similar to the monad coherence diagrams that I showed you before. So take an object, use the return map to map it into its monadic container, and then if you run the algebra, you should get back the same object, as you would expect, right? Because as we said, the eta function does not transform what's inside the object, it just packs it into a box, right? Similarly, if you have a composition of two monadic containers, you can either decide to first join them using mu and then evaluate it using the algebra, or first evaluate the inner one using the Endofunctor transformed algebra, and then use the algebra arrow to reduce the result. These two should get you to the same final object. Once again, you have a sort of associativity in the order in which you choose to reduce your containers. And now, using this construct, we can actually execute group actions. So, specifically, group actions of a symmetry group G are algebras for the group action monad G times blank. And let's show this with a simple example, going back to convolutional neural networks. Let's assume we're looking at the translation group. So our data are images, and we are shifting them in the x and y coordinates, so in the first and second dimension. So our symmetry group is cyclical shifts, and they can be defined using two numbers, two integers, one telling you how much you're shifting in the first axis, the other one telling you how much you're shifting in the second axis. And the carrier object, so the object we're acting on, is just a grid of pixels. So it's real numbers of width times height, right? So this is our A object for the algebra. And what would be our structure map is this shift operation, which will take a group action contained element. So it gives us one group element here and one pixel map here. And it gives us a transformed pixel map such that if I act on my pixel map using translation I prime j prime, and I want to look it up in position ij, it's the same as taking the original map and shifting the coordinates appropriately. Note that this must be, for this to be a symmetry, this must be a circular shift. So really we take I minus I prime mod h, j minus j prime mod w, right? But this is basically how it works. So this algebra is what gives us our translation action. And now, these monad algebras and carriers will tell us what are the possible inputs and outputs for a neural network, right? So these r to the w times h, those are the kinds of things you would put inside a neural net, either as input or as output. So now the final thing we need is we need something to connect them, like some function that will take us from one to the other, and that is our neural network, right? So to actually specify a neural network that is equivariant, we need to define a morphism that will connect our two carrier objects, and that is a monad algebra homomorphism. So that is, if you remember at the very beginning, I said we can use monad algebra homomorphisms to describe all of geometric deep learning. This is how we're going to do it. So, as we discussed, so this monad algebra homomorphism maps two carrier objects from one to another, and equivalently it maps two algebras from one to another. So let M eta mu be a monad like before, and you have A and B, which are two separate algebras for two separate objects. They might be exactly the same object, but the structure maps might be different. And a monad algebra homomorphism is just a morphism connecting the two carrier objects such that the following diagram commutes. So what does this diagram tell us? When we have a monad container containing A, we can either first reduce it to get the underlying A and then apply our homomorphism, or we can first use the Endofunctor transformed homomorphism to transform A into B inside the container and then reduce the container using the rule for B, and we must get exactly the same result in both cases. And I hope you see how if I now plug in the specific case of, say, the translation group action, so this is exactly the same diagram as here. I've just kind of plugged in what we talked about before with translation group actions or rotation group actions or anything like that. So our carrier objects are these featurized pixels, right? So width times height times some number of features k, width times height times some other number of features k prime. So these are two different spaces we can act on. And we have a translation action here and a translation action here. Our F is now a neural network mapping us from k-dimensional features to k-prime dimensional features over images such that this diagram here commutes. And once you resolve this, you get this. Does this equation look familiar? This is translation equivariance, right? And you can apply exactly the same idea to rotation equivariance, to permutation equivariance, whatever you want. This blueprint of group action monad algebra homomorphism gives you all possible equivariant maps, and this is the essence of deep learning. This now gives you a set of constraints, and you can resolve these to get your neural networks F that map your data in a way that respects the structure of the symmetry group. And maybe useful to say is you can generalize this to any pair of algebras A and B. And once you do this, once you resolve the diagram, you'll get a function, a constraint that looks like this. So a function of A transformed x using G is the same as the B transformed using G f of x. And I hope that you can also relate this to the more generic formulation which uses group representations rho x and rho z, which I gave you in lecture 1. Right? And this is all of geometric deep learning. All of geometric deep learning can be represented using this formula over here. So this is, it is a mouthful, but now hopefully we understand all the individual building blocks of this mouthful. equivariant neural networks, equivariant maps, are just group action monad algebra homomorphisms. And hopefully now every single one of those terms at least roughly makes sense. It's a good exercise now, once you know how to build equivariant maps, to see how would you specify invariant maps. The trick is, of course, to have a very specific algebra as B algebra. Have a think about that. Okay? Now, of course, once you have a constraint like this, it only tells you what is the mathematical property that your neural network needs to satisfy. It doesn't tell you how to actually implement it. In order to use category theory to tell us how to implement it, we need to plug this diagram, this equation, into a category where we work with vectors. And as we said in the previous lecture, we can use a category like vect to do this. Or, well, in general, because neural network layers will have biases and not just matrix multiplies, you might actually prefer the category AF of affine spaces. But let's stick with vect for now because it's easier to just think of matrix multiplications. So, for example, if we take our previous diagram, which has our monad algebra homomorphism F mapping k-dimensional image features to k-prime dimensional image features. Once we ground that in vect, we know that F needs to be a linear transformation, so it must be fully expressible using a matrix W, which is then multiplied with our features, right? And that very constraint, coupled with the form of the function like this, then gives you direct weight sharing instructions in W. It tells you which pairs of weights in W need to be exactly the same, and you rediscover the well-known result for shift invariance, for example, shift equivariance, that this matrix W needs to be a circulant matrix, right? As we discussed before, it's a well-known fact in signal processing that the linear translation equivariant layers are exactly circulant matrices, aka convolutions, right? I think it's a good exercise to try to derive this from first principles. So if you have some time after the lecture, take the special case of 2 pixels. So weight is 2 and height is 1, and see which constraints you get for W in that particular case. Okay, so this was the first result I wanted to show you. It took us about a lecture and 10 minutes, but we have been able to rediscover everything we've done so far in geometric deep learning using this new concept. And that's great, but I do have something to offer here which isn't just a new perspective of looking at something you already know, because when I defined this monad algebra homomorphism, I haven't used the monad axioms anywhere, right? Let's go back to this diagram for a second. There is no eta and no mu in this diagram anywhere, right? I'm not explicitly using the fact that my endofunctor M has this extra structure attached to it when defining my algebra homomorphism. And that strongly suggests that I can generalize what we just did to go beyond monads and into arbitrary endofunctors. And that will actually be our first step to go from simple group equivariant models into the realm beyond. Okay? So to do this, let's define what an endofunctor algebra is as opposed to a monad algebra. So we take any endofunctor F which maps category C to itself. And an endofunctor algebra is, as we had before, a pair of a carrier object A and a structure map lowercase a. And that's it, actually. So in this case, there are no structural constraints that you need your model to satisfy. And actually, this is a much simpler and more generic object to work with. And if you've covered some category theoretic foundations of computer science before, you might know that actually examples of these endofunctor algebras are super abundant and they express fundamental objects in computer science. Let's start with lists. Lists are a very standard object you encounter in one of the first computer science courses you cover. So how can we describe lists using endofunctor algebras? Let's have A be a set. This A is a collection of all possible objects that could go into our list elements. And we'll define an endofunctor 1 plus A times blank, which maps set to set, just as before. And list of A is going to be a set of all possible lists where the individual elements are from the set A. And specifically, we also need a way to describe two special constructors for a list, and those will be our structure maps for an algebra. The first one is called nil, the second one is called cons, and they deal with the two parts of this set structure. If you haven't seen the plus notation before, it's basically a disjoint union. So either you have something that is a single element set, which is nil, empty list, or you have an element A combined with a list containing the remainder of your elements, right? And this nil cons maps this overall construction into just a single list using the usual constructor you might see in Haskell, for example, right? So what is a list of type A? It is either an empty list, which is the nil part that maps 1 to list of A, or cons A and list of A, which maps this construct, this product here, to just one list. And that, so list A as a carrier object and nil cons as a pair of structure maps, is an algebra for this endofunctor. All right? You can convince yourself that it's a proper, that list of A is a proper, sorry, that 1 plus A times blank is a proper endofunctor, and that these objects satisfy the constraints you would want. And what's very nice about this endofunctor is that it describes lists in an inductive manner, right? Either as an empty list or a concatenation of one element of type A with another list. This is very typical in functional programming languages. You can also do similar things with trees. Note there is, very minor changes from this slide to this slide. Now I'm looking at A plus blank squared to describe binary trees with A labels on the leaves, right? So tree of A is now set of all binary trees with elements from A in the leaves of the tree. And we have leaf and node as our two structure maps, which will take either something of type A and wrap it into a leaf tree, or it will take a pair of trees and wrap it into a branching node, which maps into the two trees as a left and right subtree, right? And then, once again, this combination of tree of A as a carrier object and leaf and node as structure maps is an algebra for this particular endofunctor A plus blank squared. And once again, just like in the case of lists, it describes trees in an inductive manner, either as a leaf node containing an element of set A, or as two subtrees, a left one and the right one. Now, of course, this is a very particular way to represent trees, which forces them to be binary and puts no labels in the intermediate nodes, only in the leaves. So it's an interesting exercise to think, what would you need to change in this endofunctor so that you can specify trees with labels in all the nodes, or trees which have a variable branching factor. These should be relatively simple exercises if you just follow the derivations from this slide and the previous one. But I feel like they're useful exercises to do if you want to kind of verify that you're confident in these concepts. Okay? And just as before, the same way we defined homomorphisms of monad algebras, we can define homomorphisms of endofunctor algebras. Really, the diagram is exactly the same. Nothing has changed. We take two different algebras, and we have a map that maps the two carrier objects in a way that this diagram here commutes. And one classic example of an endofunctor algebra homomorphism is a standard operation you might do over a list, which is known as a fold. You might have heard about folds before. So what they do is they map from list of A with nil and cons as the two structure maps to some carrier set X with structure maps R0 and R1. Once again, you need two functions because there's a plus here. So you need to have something which acts on the 1 and something which acts on the A times X. And both of these are assumed to be endofunctor algebras for this particular endofunctor. So this is plugging all of those things into the diagram I've showed you here. So just plugging all of the applications here. And what do you know? Now you can have this f of r, which maps data that lives on a list, which might go in a neural network, to some output x, which might come out of that neural network once you've processed the list. And this gives us list equivariance constraints. Specifically, if we know we would like to align our neural network with a fold operation that has functions R0 and R1, this directly induces constraints that the function, our neural network applied to the empty list, should give us the same output as R0 applied to the unit set. And the function, our neural network applied to a cons of head and tail, is the same as applying a different function R1 on the head and the recursively applied neural network on the tail. So these are now new equivariance constraints that a neural network FR needs to satisfy in order to be a valid fold over a list, which aligns itself with R0 and R1. So this is a standard example of algorithmic alignment, right? We have an algorithm that performs a fold and does operations R0 and R1. You want to build an algorithmically aligned list neural network, it must satisfy these two constraints. And this is similar in spirit to group equivariance, but I hope you can see that we could never have derived rules like this using geometric deep learning. Why? Because we had f of g transformed input is the same as g transformed output, but consing h to a list is not a group symmetry operation. It adds extra data to a list. So it's not a symmetry, right? So cons does not leave a list unchanged. It is not a symmetry, and this is not something you can recover from groups. Now, hopefully it's not too difficult to then take this idea and apply it to folds on a binary tree. I could have re-derived this from scratch in the lecture, but I felt it was similar enough that you can take the idea of how it was done for lists and re-derive the constraints for trees by yourselves. Now, one thing that gets really interesting when we talk about endofunctor algebras is we can also study the dual concept of an endofunctor coalgebra. Now, coalgebra might sound weird if you've never come across opposite categories and things like that, but it's really a relatively simple concept. It is just hunting for algebras, but reversing the directions of all the morphisms that we're looking at, okay? So once again, we have an endofunctor, which maps a category to itself, and we have a pair of carrier object and a structure map. But now we have a coalgebra, which means that our structure map doesn't map f of a to a, but the other way around. It takes an a and wraps it into f of a, right? And what does this mean intuitively, and why is it so important for computer science, is execution of algebras is something that kind of guarantees you terminate, right? We had a fold algebra, which iteratively looks at one element of a list at a time and processes them all together and terminates when you run out of elements, right? But here, we constantly produce additional objects, so we're guaranteeing productivity as we're iterating this A. So really, coalgebras allow you to represent computations that are repetitive, productive, and potentially infinite, and therefore they're a fantastic way to represent automata, which are basically the stepping stone to computers. So you can use this to express things like Moore machines, Mealy machines, streams, even Turing machines. So let's use Mealy machines as a standard example. Hopefully, at least some of you have covered in the computer science undergraduate courses the concept of Moore and Mealy machines. I'll quickly survey what a Mealy machine is as we go through the slide. So we can express these kinds of automata, like Mealy machines, as endofunctor coalgebras, right? Specifically, we look at this endofunctor here, an endofunctor that represents functions that take an input and produce an output and return blank. Once again, this is a mapping in set to set, and specifically the set Mealy OI of Mealy machines that have outputs in the set O and inputs in the set I are a carrier object for a coalgebra which maps a Mealy machine to a function that takes an input, gives you an output, and gives you a new Mealy machine. So the idea of this is I give you a machine in a particular state, I feed it an input, and then that machine will react to that input by producing an output and an updated version of itself, right? It will change its state, its registers, whatever, right? So this is really a function that you can iterate infinitely and just loop this computation for new inputs that are coming in. That's the idea. Or in Haskell terms, you can define it as this particular data structure. So specifically, it's a data structure equipped with a function next, which takes an input and produces output and a new machine. Now, the same way in which folds over lists allowed us to, list algebras allowed us to describe lists in an inductive manner, this construction describes Mealy machines in a co-inductive manner. So it's a system that, given an input, produces an output and another transitioned Mealy machine. And just like you had algebra homomorphisms, you can also define coalgebra homomorphisms. But the main difference is, remember, the arrows are reversed. So previously, we would have a function from a list to some output x. Here, we have a function from x to Mealy machines. Right? And once again, this is just me plugging into the reversed diagram for Endofunctor algebra homomorphisms, what this looks like in the case of Mealy machines and this particular Endofunctor. So what we actually have is we have a Mealy machine with its next function that does some production rule, and we would like to map from some particular carrier object x into a Mealy machine using our neural network, such that we can iterate the repeated computation of x and then make it into a Mealy machine by mapping the resulting x. Or we can map x into Mealy machine and then run the usual next function, and those two should give us the same result. So we end up with coalgebra equivariance constraints by resolving the commutative diagram. We need to have a separate rule for the first and the second output of this function. But we can basically say, how does our neural network, Fn, which maps a specification of our inputs to a specification of a Mealy machine, how does it map from our input space to something that the next function would accept? These are the two things that must be satisfied. Once again, we are looking at something that is an equivariance constraint, but it's one that generalizes group equivariance, because the transformations here that we have on the left and the right are definitely not symmetries, because they keep producing new stuff. They keep producing new outputs and new machines with new states. So there's no way that these things are symmetries, right? And this is a possibly infinite automaton that need not be invertible. As a result, you would never have been able to get these constraints from geometric deep learning. And now our Fn is the neural network that we're looking for. And once again, an interesting exercise is Mealy machines are actually a bit more complicated than Moore machines. Moore machines are typically assumed to be stateless. So one good exercise is, could you rediscover what these constraints would look like if I gave you a Moore machine rather than a Mealy machine on the right-hand side? Okay, now I want to briefly outline some issues with the picture as we've looked at it so far. So we went from group equivariance and then generalized beyond that to arbitrary structured computation, both algebraic, which kind of summarizes an input object, and coalgebraic, which infinitely produces stuff in response to inputs. But the approach so far does leave a few things to be desired, and these were problems with geometric deep learning as well, actually. First, so these things will give you constraints on neural networks, in this case f of n, but you still need to find a way to write a neural network that satisfies this constraint. And so far, the way in which we were able to do this is by assuming our diagrams lived in something like vect, where our morphisms, our neural networks were actually linear, and there we were able to kind of sometimes resolve for these constraints in the linear case. GDL, by the way, is no better. All of the constraints we looked at GDL, as we said from the beginning, are linear equivariance constraints, and then we're usually like, okay, you take a linear layer, you compose it with a nonlinearity activation, and that's then enough to represent everything you need, right? So both our approach so far and GDL can only ever give us linear layers, and we cannot reason about entire architectures very easily by just mapping into vect. Well, one caveat is that we can use these constraints to do things like data augmentation or loss functions, and that can be useful to kind of optimize an architecture towards this behavior without explicitly solving for the constraint, and that might sometimes be enough. but we cannot really reason about what does a solution to these constraints look like in neural network space. Another issue, which is intimately tied with this first issue, is that we cannot easily explicitly reason about parameters of an entire network. So the actual weights that go into layer 1, layer 2, and so on, and how they relate to each other. And arguably, talking about parameters is pretty critical because you need them to model the forward pass and the backward pass of a neural network framework. In order to talk about these things, we need to go beyond one categories into two categories. Now, this jump is not as scary as it sounds, at least not in principle. The main difference is that, unlike in a basic one category where we have objects and morphisms, in a two category we also have a notion of a two morphism, which is a mapping between morphisms. And actually, we have already secretly been working in a two category, perhaps without realizing it, the category cat, which has objects that are categories, morphisms that are functors between the categories, and two morphisms, which are natural transformations between functors. So we've sort of been describing a two-categorical framework from the beginning when we talked about natural transformations. We just did not make it explicit that we were doing any of our stuff inside cat. But actually, jumping into two categories now allows us to kind of tensor up our computations and include explicit treatment of neural network parameters. This is a relatively recent construct in applied category theory. The first kind of publications around it started arising in about 2 years ago. And specifically, we look at the two-category para, which is the parametric morphism category. Now, para is actually very similar to set. The objects of para are the same as for set. The objects are sets of possible inputs and outputs for different functions, right? But our functions, our morphisms, are now parametric morphisms. So an f doesn't just live by itself, it also has some parameter set p attached to it. And this is now a mapping from A to B, which might be parametrized by a set p. So how would you recover original set category from this? You just say that p is always the empty set, right? These are the functions without any explicit parameters specified. And specifically, how does it work? This pf is a morphism in para if p times a to b is a morphism inside set, right? Because we really just treat these parameters as extra inputs to our function, something that tells us how the network will react. If you've programmed in a tensor framework like JAX, it forces you to be explicit about the parameters you're passing into every single function. So hopefully, at least for some of you, it will not be a strange concept to pass parameters as extra inputs to the forward pass of a neural network. Some frameworks might hide this from you, though, but it always happens under the hood. And one thing that's nice about these paramorphisms is that you can nicely draw them as this block diagram of A to B, which takes the parameters as an extra specification. And of course, as we discussed before, you need to talk about not just your morphisms, but how the morphisms compose. And well, in this particular case, using the diagrams, it's actually quite easy to intuitively understand how these morphisms compose. So imagine I have two parametric functions, f and g, which map A to B and B to C, respectively, and they take parameters from a set P and set Q. I can then basically compose this by taking one function that maps A to C and takes the tensor product of P and Q as the overall parameters, and then kind of secretly under the hood, the P parameters go in step 1 and the Q parameters go in step 2. And one thing that this parametric construction now allows us, which we couldn't do in the set category, is we can also talk about two morphisms, so maps between parametric maps, and those are reparametrizations. So basically, can I specify a function from A to B, but using a different set of parameters? And you can do this using this reparametrization map R, which maps a new set of parameters to the original one. And once again, the block diagram hopefully makes it quite simple to see how you can apply this two morphism, right? So this R, which maps P prime to P, gives us a mapping from F to FR, which is a reparametrized function. And this is now a two-morphism because it maps the original F box to the FR box. It's a mapping of those two guys. Reparameterizations are a really cool concept because using them, we can talk about weight sharing not just inside one layer like we did in GDL so far, but also across layers. If I want to say two different layers have exactly the same parameters, all I have to do is go from a P times P, F, which is now, two layers that take parameters from exactly the same set, and I reparameterize them using my two-morphism, using a copy parameter map, right? Now I suddenly have an X to Y, which has the same backbone as F, but it only takes a single P as input, not a P times P. And my copy map is what allows me to put the same parameters in both parts. So I can easily talk about weight sharing using this idea of the two-morphism. Now, this is a beautiful category to work with, and you can now use it to express not just properties that neural networks must satisfy, but also their implementations, because these neat little block diagrams tell you how different layers of a neural network stack up together with their parameters. This is not something you were easily able to do inside SET. However, jumping into a two category also makes it much more complicated to talk about what a commutative diagram is, because we previously only ever dealt with this type of diagram, which is a proper commutative diagram where any pair of paths must be exactly the same transformation. But now that we're allowing ourselves morphisms between morphisms, we also have different notions of what commutativity might mean, because we can have a situation where, okay, there are two paths, but I can find a two arrow that combines this path to this path and this path to this path. And this is also a form of commutativity, just a slightly weaker one than what we had initially, right? So specifically, in two categories, there are four possible situations you might find yourself in, depending on whether your paths are exactly equal, whether there's an isomorphism between them, and whether there's a two-morphism pointing in one direction or the other direction between the two paths, giving you these four situations: commutative diagrams, pseudo-commutative diagrams, lax commutative diagrams, and co-lax commutative diagrams. By the way, this is not something I'm going to deeply dive into. This is just so that you have a feel for the complications that arise. I will share at the end of this talk a recent paper that we published. It has a very hefty appendix talking about these details from the basics onwards to the specifics. This is just for you to appreciate how, okay, we can track parameters by jumping into two categories, but now we need to deal with more complicated commutativity diagrams and constraints. And we are actually certain, we're reasonably certain, that all four of these types of diagrams will yield interesting architectural rules and interesting neural network architectures. But in the paper that we just now released, we only focused on the lax commutative algebra homomorphisms. So we take the diagram for the usual Endofunctor algebra homomorphism, but we add the constraint that these paths don't have to be equal, but there just has to be some two-arrow reparametrizing the functions from here to here, right? And just by focusing on the lax two algebras in para, it is sufficient to recover all different types of weight sharing you might want to do inside standard folding recurrent neural networks, recursive neural networks, and also these automata-style neural networks like Moore machines. So I won't go into the details of how these things are derived, but just the thing you should understand from this is that just by focusing on this picture, we can rediscover all of these data flow diagrams. Now note the subtle jump that we've done. Throughout geometric deep learning and throughout the first part of this lecture, we looked only at constraints, at semantics, so explaining the property that a function has, that a neural network should have for it to be appropriate for a certain kind of input, with certain kinds of symmetries or other equivariance constraints. Now, using the two algebraic lax algebra homomorphisms, we can actually also talk about syntax. Like we can talk about constraints about which weights need to be exactly the same for this architecture to satisfy a particular constraint. And we rediscover things like RNNs, and for the first time we can talk about weight tying in two different layers. GDL was not able to tell you this. right? Or at least it wasn't able to tell you how to do it. Now, if you should take away any impression from this, is that this categorical deep learning picture is very rich and only formed recently. By recently, I mean this paper came out on the archive today, like at 1 a.m. today. I was really trying to make sure you have a reference before I give this lecture. It was something we've been working on since a few months before the course started. I was really hopeful it would make it in time for this lecture, and we managed just in time. So it's a picture that needs to be built. We have shown the building blocks. We've shown it can go beyond GDL, but now we need, we need people to take this idea and show what are all the amazing things that can be done with it. So we invite you to contribute. Please go to categoricaldeeplearning.com if you're interested in any of this, and there you can find our paper on the archive, the Cats for AI course, which we've given in preparation to doing this work together, which covers the basics of category theory for machine learners. And also, there is a very neat GitHub, which has lots of paper pointers to all the ways applied category theory has been used for deep learning so far. This is joint work with Bruno Gavranovic, Paul Lessard, Andrew Dudzik, Tamara von Glen, and João Araújo. And yeah, I'm really looking forward to see what you make of this. Now, if during this journey, as you probably will, you will come across a term that's not very nicely explained and you would like to understand it better, there is a resource you can turn to for this. It's called NLab. I heard laughter, so some of you already know what NLab is. Arguably, I would say it's the best resource. It's like Wikipedia for categories. But one thing that you should really bear in mind is that NLab is written by mathematicians for mathematicians, and articles are not written in a way that gives you intuition most of the time. It just sort of assumes you know everything else other than the thing you're reading. And therefore, whenever I go on NLab, if I'm not careful, I end up in a rabbit hole that lasts for 2 hours or longer. So beware of rabbit holes. Try not to dive too deep if it feels like a concept is too tricky. Rather ask someone than keep diving deeper. But this is a great resource that we repeatedly used during